Okay, well, welcome everyone. I have the pleasure of introducing our speaker for this week's College of Science Center for Imaging Science seminar series. So my name is John Karakis. I'm one of the faculty here in the Center for Imaging Science, and I had the pleasure of meeting Professor Jun Wang almost a year ago at the fall AGU meeting, where we had a lively discussion about air quality and aerosols and remote sensing. And following that up, we thought it would be good to invite him to speak to our department. And we've also arranged a number of side meetings where he's had a chance to meet with some of our faculty. And I think he'd be willing to have more if there was additional interest after this seminar. So just a little background on Professor Wang. He's the James E. Ashton Professor in the College of Engineering at the University of Iowa. And his primary appointment is in the Department of Chemical and Biochemical Engineering, and he has appointments in the Department of Civil and Environmental Engineering and the Department of Physics and Astronomy. He received his BS in Atmospheric Dynamics from Nanjing University of Information Science and Technology, and his MS in Mesoscale Meteorology from the Institute of Atmospheric Physics, Chinese Academy of Sciences. And then he came to the US and received his PhD in Atmospheric Sciences from the University of Alabama, Huntsville. For a few years, he was a postdoctoral researcher at Harvard University. And of course, now he is at the University of Iowa, where he leads a team of researchers on the topics that he'll be speaking about. His research focuses on the integration of satellite remote sensing, Earth system models, and Internet of Things to study air quality, wildfires, land-air interaction, weather, and climate. And has authored over 145 research articles, co-edited 2 books, and supervised 20 undergrads as well as graduate students. So he's well-versed in academia and speaking to students, and we look forward to hearing from him today. So with that, Professor Wang, please go ahead and get started.
All right, thank you, Professor John Karakis. I met with John last AGU in December 2019. We certainly weren't able to predict we're going to see and give us exchange our research in a manner that we never were thought at that time. So I hope everybody is doing well in the Northeast, and it's a very great pleasure to share with you some of my work, my team's work through this virtual environment. In some way, it's good because I can save some travel time and spend time just with students or with the family. So thanks a lot for having me. Today, I'll be talking about the solar remote sensing of fire combustion efficiency and the smoke plume height. And I will get started first by kind of do a quiz. Really hard to do a quiz online these days, but I'm not going to do a quiz really ask you to like give me an answer per se. But let's say we often, when we have a birthday party, we have our candle light up, and then we'll have our kids or ourselves will blow out the candle. So the question is that why does a candle blow out? A, our breath is mostly CO2. We need oxygen by our body, and then we breathe out the CO2, and the CO2 certainly is a killer for fires, right? And as B, our breath is cooler in the environment. You know, our normal body temperature, 37 Celsius. So it's not hot enough for fires. C, the wax paper, the flaming part is moved away. Anyone want to give a shot? Or I don't know how to do this, but anyway, you can type in the chat or maybe, I see 2 here, let's see here. Okay, most of you select C, that A plus C, okay. Well, I think the C is the physics, from a physics point of view, it is right. The reason is because this part is a flaming. Let's see here, can I get the laser here? Pen here. So this part is the, yeah, okay. I don't know why this, okay, this part is a flaming part, and there are a lot of gases there burning it, a lot of chemical reactions to it. So when we blow them, the air moves. This part of the flaming part goes away to here. And as a result, it cuts the supply of the fuel from the candle to the part that is air is hot. Therefore, the candle is blown away. So that tells you something is that the flaming part is very important to sustain the fire growth and the fire expansion. If just like this, we call the flaming, we call it the smoldering. If the smoldering, then it's hard to make the fire to move around. It will be stay there and mostly will be dying. Also, you notice that when in the smoldering phase, you see this smoke coming out. Those are very whitish color, and you don't see that when you have a flaming, when the candle is in light with the flaming. Okay, so this is kind of intuitively, you see the physics here. So the fire needs three elements: the fuel, the oxygen, and the heat. And so in the past, the scientist has been studying the fires, I mean the natural fires, wildfires, by using all sorts of the methods. Some of them are from the aircraft and satellites. Some of them are collecting the samples and studying in the lab. And this is one of the pictures I took when my team participated the NASA's Fire XAQ campaign last year. Unfortunately, last year we didn't have not much of the fires compared to this year, but anyway. And then you also have trailers that collect a sample to try to understand the fire impact on the environment. If we think about it, the fires actually emit a lot of things. Most of them goes to carbon dioxide, right? 90 or 95% of them, depending on how complete the combustion is. But most of them goes to CO2 in terms of mass, carbon mass. So, and we know CO2 is a greenhouse gases and will remain there for a long time in the atmosphere. On top of that, if it's incomplete combustion, some of them will also go to carbon dioxide. And eventually that carbon dioxide will become CO2 and remain in the atmosphere, become greenhouse gases. In the process, carbon dioxide will also help and promote the ozone formation at the surface, which is also makes the air quality bad. And certainly, the smoke particles is bad for air quality, bad for our the visibility and things like that. So what I'm going to talk about today primarily want to use satellite data to study some of these things that you may be able to get from aircraft or from a trailer or from the lab. But you cannot get that globally everywhere where the satellite can provide. If we can get those from satellite, then we can have a global mapping of all the properties about the fires. So on the satellite, what satellite sees is an electromagnetic wave that caused by or emitted by a fire, right? So in the past, I would say probably 4 decades, we have made a lot of progress to using satellite to monitor fires, to study the fire properties. So the underlying principle here is basically the Planck function curve, right? Which I assume many of you have learned before in the class. The Planck function basically says is that when a temperature, given a temperature of the object, that object will emit radiation in all wavelengths. However, when the temperature increases, then the intensity of the radiation in the shorter wavelengths will increase more rapid than in the longer wavelengths. You can see here, as the temperature increases, all the intensity increasing all wavelengths. However, the rate of the increase in the shorter wavelengths is much faster than the rate of increase in the longer wavelengths. So when you get to the point where you start to have fires, then the shorter wavelengths intensity will be larger than the longer wavelengths. So in our planet, normally most of the peak of the emissions is around 10 micrometer. So we can see here we can use 11 micrometer wavelengths. And so in normal days, without any fire, 11 micrometer intensity will be much bigger than the 3.7. 3.7 will be somewhere goes to all the way to here. You cannot see it, okay? However, when they get to the fires, you can see 3.7 will be larger than 11. So that kind of is a kind of a physics behind it, that we can use 2 wavelengths or multiple wavelengths to characterize the fire from a infrared channels. So in the last 4 decades, we are able to characterize the fires in cloud-free conditions. If you have cloud, then that cloud will absorb the infrared radiation, and so you cannot see through cloud and see the fires at the surface. And in cloud-free days, we are able to characterize the fire burn area, fire radiable power. This is a very key concept, basically saying that how much radiable energy or how much radiable power is generated given a certain time when the fire is burning. So we know in the physics, normally the mass versus energy somewhat correlated, right? So if you have more burning of the mass, generally you generate more energy. So that power or energy, depending on how you look at it in different certain time, the energy in different certain time is power. When satellite could overpass it, they pass over that defined moment. So the satellite give you a power, not necessarily the energy. But you can always assume fire does not change within a certain time period, you get a power. Now from there, you try to estimate how much mass, how much fuel are consumed by the fire. That is important because we want to estimate how much CO2 are emitted, how much CO are emitted, how much small particles are emitted. That emissions amount matters because it affects climate, affects the environment. So then certainly most of the fire is actually smaller compared to a solid pixel, right? We are talking about like MODIS or VIIRS type of satellite, 1 kilometer resolution. Most of the fires are smaller than that. So there is also argument try to develop to study the temperature in the fire area within that pixel. Then you also have the daytime plume height from the fire sources in here. I'm going to talk a little bit more on here. We have done a lot of work trying to study the injection process. Anyway, from here, you can start to look at the emission estimate and the fire surveillance and things like that. So most times so far, you can see those techniques are based upon infrared. And one of the things we try to kind of push the research kind of frontier a little bit is try to study the fire phase. So far you can see here, there is no data give you the fire phase. Is it flaming or smoldering? When we say smoldering or flaming, it's kind of binary, right? But in reality is that you can have a fire, you can have a pixel here, and maybe part of them are flaming and part of them are smoldering. So when the satellite sees it, sees something that is a mixture of both. So you want to characterize not just flaming or smoldering, just not in a binary mode, but you actually want to characterize the combustion efficiency. If it's a 100% combustion efficiency, then everything goes to CO2. Then the rest, if lower than 100%, part of them go to CO, part of them go to the small particles and such. So we want to study. So in the past, the satellite data has been given us the fuel and heat concept. But what we also want to study is about how the oxygen plays a role in this process, right? The complete combustion will use more oxygen than incomplete combustion. So these are the things that we try. I try to highlight some of the work we have been doing so far. So why this matters, right? So if you look at this fire here, you will find this part is flaming, which I already talked about with the example of candle. The smoldering in the real part, in the real fire, most smoldering is occurring near the surface where you don't have the oxygen goes into it, right? Very hard to have oxygen, have a wind coming down and have oxygen coming, enough oxygen to make it flaming, very difficult. Where on the top of here, you can have the wind coming, you got oxygen to provide, to make them flaming. So most smoldering is actually near the surface. And there are a lot of chemical processes going on here, and I'm not going to go to detail here. The point is that when in the atmosphere, you will have the flaming part, that they will emit the visible radiation. And that's basically is the key criteria when we say this part of the fire is inflaming, because you got to have a visible light. Without a visible light, according to definition, it's not going to be inflaming phase. All right. So why this matters? Well, here is basically I'm showing here is a ratio of CO2 divided by CO plus CO2. That's called the combustion efficiency. We call MCE modified combustion efficiency. So if everything goes to CO2, there is no CO, this MCE equal to 1. When you get to the incomplete combustion, you got more CO, right? And you got less CO2, and this curve goes to here. So according to the aircraft measurements and lab measurement, you can see when the MCE increase from 0.88 to 0.96, you can see the organic carbon decrease a lot. Those are called emission factor. Basically, per mass, per unit of the mass of the fuel combustion consumed, how much goes to, what's the fraction goes to organic carbon, for example. So the unit here certainly is scaled a little bit more. So so is multiplied by a factor, maybe 10 or 1,000. But anyway, what matters here is that when your MCE increases, you get a more complete combustion. You got less organic carbon. Remember, I talked about this candle, right? So when you have more complete combustion, the organic carbon mass basically is gone. You don't see that whitish smoke coming out. As a result, you see more elemental carbon. You see more sulfate particles going up in the trees, and we do have sulfate SO2 that's going up, and the elemental carbon to organic carbon ratio also increases dramatically. In this case here is that this elemental carbon, this soot particles, is actually generated as a byproduct of the flaming process. So when you have more flaming, you got more complete combustion, you actually have more organic, you have actually more elemental carbon, and those are soot particles, and those are dark smoke particles, and they will absorb strongly of the light and make the atmosphere hotter, right? And so here shows what we should call the single scan albedo, basically indicate if the particle is very reflecting the light, then single scan albedo is close to 1. You can see when the combustion efficiency increases, as a result of the increase of the elemental carbon, this single scan albedo decreases a lot. So it's absorbing a lot of the solar radiation in the atmosphere. That is why it's so important to characterize the fire combustion efficiency from space. And so far, in the global model studies or global climate model predictions, we just using 1 or 2 typical values. That's it. We are not able to get this for each individual fires. So the way we try to study the fire combustion efficiency is to rely on the principle that if you have light, then you have part of them are in the flaming. You have more light, then that means you have more fraction are in the flaming part. So luckily we have this satellite called VIIRS that was launched in 2012. And you can see at that time, those are the light in city lights, right? Boulder, Denver. You can look at here, these are high park fires in 2012. So when I ask students to plot them, immediately you'll find, oh, actually you see the fire light from space. So we were very excited about that. And then we can say, well, can we use that to calculate the fire combustion efficiency? So certainly this gets to a little bit of the mechanics side of the things for any imaging sensors. Like VIIRS, it's able to detect the low light at the nighttime. And the VIIRS actually have many bands. And the day and night band, the one that can see the light at night, is actually collected from a 2-dimensional CCD array, where the rest of the bands are not 2-dimensional CCD, they are scanners. So as a result, in order to detect the fires, because the fire pixels are pretty localized, in order to really know the temperature and the light coming from that fire pixel, we have to align the pixel from this bands, infrared band or visible or other band, near infrared band, together with the Terra band pixel, line them together. And we have to remove the Baute effect and things like that. I assume you have learned that in your class, right? So here is a river. If you don't remove a Baute effect, you see these two rivers. You see this river, this part and this part are kind of overlap. Your image could basically have a pixel overlap for the same location. You can detect. The implication for fire detection is that you are double counting the 5 pixels. So we want to remove that. We did a lot of work try to mechanically align the data collected by Terra band versus other bands, because Terra band, although it's in the suite of the satellite, suite of the instrument, but this band is separate from the rest. So their focal plane is different and such. So nevertheless, we did a lot of mechanical work on that one to align the thermal and the infrared, near infrared band together with Terra band together. Okay, here is kind of the approach here. So once we align them together, then you can calculate two quantities. One is called the visible light power. This is defined as based upon the intensity of the light you get in the visible. You can then multiply by the pixel area, assuming that the light coming out is more or less a Lambertian. Then you can estimate the visible light power. Then you can use this visible light power divided by the fire radial power. Remember, in the beginning, I just talked about the fire radial power is something we can calculate from satellite using thermal, using 4 micrometer channel. So basically, this quantity called the visible energy fraction basically tells you that well, the fire is emitting visible energy, but also emitting the energy in other wavelengths. So within the total amount of the retrieval energy, how much is consumed by the visible? That is called VF. And you can imagine if it's highly complete combustion, then this part will going up because you have more energy goes to the visible light in the visible spectrum, where you have less goes to the other bands. You temperature get hotter and such. So we then try to establish the link of what you can got from satellite, which is VF, to something that the atmospheric chemists want, or modelers want, or something that you can more tangible, which is called the modified combustion efficiency, which I just showed in the previous slides. This one then can get to the emissions, right? You can see the you can get to the emission factors, and then you can estimate how much CO2, how much CO, how much carbon, black carbon, organic carbon, and such. So here I just want to share you some results here. You can see here what you see here is that this is 1 year of the data. We are showing here the visible energy fraction VEF. Immediately you see, oh, VEF is actually pretty has a large range here. If you look at the Middle East, and this part right here, and this part right here, you see very high visible energy VEF. Why? Because this part are all gas flares. You see the Gulf of Mexico. These places are all gas flares. And then you see here, two gas flares. Gas flares certainly is used by the petroleum industry, right? Oil industry. So they have to burn them, and they just left as the bone as a residual. They just burn them. So they are very in high complete combustion. So we see that, but we also see the fires in other places, like in Australia. The VEF is much larger than, say, North America. Are those real? Are those reflect the surface type that we know, or this something we need to be verified, right? So we plot this one here. This is a land cover type. Clearly you see, oh, here you got a lot of shrubland in Australia, and here you got the Amazon forest. You start to see that a land surface type now reflects the VEF that I derived from space. They kind of match pretty well here. So that makes sense. That's a good sign. So what we do is then we compare our VEF with something that we don't know for each individual fire pixel, but something kind of generally on an annual basis what that MCE look like. So there are people are trying to model that based upon our best knowledge to derive that, to project that. So this is something is actually from kind of a best of our knowledge, right? Best of the, kind of best part of the knowledge to do that. So you can see actually this matches pretty well, right? If you look at by different regions, you can see the correlation and they are statistically significant, right? So you can compare them by region, and then you can also compare them by the different surface type. And this one that actually does not change that much, right? These two best fitting actually does not change that much, even by different region or by different surface type. So anyhow, this one is actually turned out to be pretty robust. So that kind of give you information is that this relationship may be able to help us to characterize on the individual fire basis, is that fire is in the flaming or in the smoldering, or what's the combustion efficiency, right? So give you another idea why this VEF is unique. You can look at this one, FRP is fire radial power that we normally get from satellite. You can see in in California, North America, versus Australia, they all look the same. Look at these two data sets, their FRP is the same. That means the total amount of radial energy that emitted by these fires in both regions, they are similar, okay? But when you look at VEF, they are different. Because here you can see this yellow part goes to here, right? It's called urban shrubland. Where over here, you got a lot of need leaf forest and other type of forest. So sure, when you have a wildfire in the forest, the combustion efficiency is much lower than in an urban shrubland. In other words, this fire radial power does not give you that, where this VEF gives you that information. So we also went to a deeper, kind of to see really does not make sense or not, because sometimes it's very hard to convince your reviewers or your peers, and that's generally the case, right? So we want to make sure things are solid here. So you can see this is a campfire in the 2018 as a time of different days here. What I'm plotting here is FRP time series, and then I also plot the VEF. What you notice that according to the FRP, looks like the fire should be most intensive on the first day when it gets started. But when you look at VEF, you find out that most combustion, most of the flaming should be on the November 11th, right? So we want to know, does this actually make sense? Well, there is a weather station about 20 kilometers away from this area. And then measure the humidity and the wind speed. You will see that on the November 11th, the relative humidity goes as low as less than 25%, where your wind speed goes as high as 7 meters per second. Where on the first day, right, on November 9th, the wind speed is half of that, where the relative humidity is also wetter than on the November 11th. So this makes sense is that we also have some other evidence that to show the weather systems. Basically, what happens is that the wind, the dry and high wind speed is actually come down from the mountains to here. As a result, the fires is more in the flaming phase compared to normally you get the wind from the coast, from the Pacific coast. So that's also makes sense a lot. So, so we not only able to use the visible light at night to describe at the pixel level the fire combustion efficiency, but also we are able to better detect the fires. The reason is because for the traditional method to use the infrared channel to detect the fires, you have to know the background temperature, right? If the background temperature is pretty high, then you need to separate you need to make sure the fire pixel temperature is also certain degrees higher, probably about hundreds of degrees higher than the background. The point is that if your background temperature is not well known, or your background temperature is not well characterized, then you will miss a lot of fires. On top of that, infrared radiation is always smeared by the background, right? The fire infrared radiation emitted by the fires can be smeared by the background and it can be affected by the atmosphere a lot. So we find if you use an invisible light at nighttime, and you are able to detect much more cooler and smaller fires. And we actually find in this case here, this actually is one of the largest fire event in California before 2020. You can see these are the standard product. This is our product. Certainly, our product give a much better description of the progression of the fire lines. This is a USDA, by the way. This is a USDA kind of a map showing the progression of the fires. But these are not done in real time per se. These are really backward analysis. This can be in near real time. We also find that we can detect the fires 2 days early than the standard product. This is actually a pretty big deal in my mind. If we can see that first light of a fire at the middle of the night, and we can go there to kill the fire before it grew bigger, it will save a lot of damages, right? A lot of down the road. So so I think firefighters are really need that kind of information there. So anyway, we find with our method we're able to detect the number of pixels by more than 90% because this standard method missing a lot of smaller and cooler fires. So how do we verify that? We verify that by using aster images, which is at the 30-meter resolution, similar like Landsat. But they, you can see that, getting to 30 meters, you can see that our detection of the fires can be verified by those fine resolution images. Images that tell, okay, this is actually what you detect is consistent with aster data, and the operational algorithm is missing that. Okay, here I give you another example. This was one of the days that in the last year when we during the VIIRS IQ Fury campaign, you can see that those are the operational product. Even in the operational product, daytime they detect 158, nighttime 171 data pixels, total 329 pixels. So the common assumption that the fires there are less fire at nighttime may not be valid in many cases. So really depending on the meteorology and depending on the situation, specific fires. We often assume the fires are not, maybe they are decaying or not growing at least at nighttime. May not be the case. Even from the operational product, you can see there are actually more fire pixels at nighttime than in the daytime. When you look at our research here, you can see we are able to detect much more fires and better describe the fire progression from here all the way to here. So you can start to see better detection of the fires. So here I give you 2 examples. Here is that those are basically one fire start from here and it goes to 2 directions. Another fire start from here, went into 2 directions. So that will be very helpful. Try to kind of help the firefighters. How do you fight the fires? So you can look at this, our VF here. You find, oh, VF here is actually pretty large. VF here is very large. And also you got something here pretty large. So in that case, that means these are the nighttime, remember, right? Now we can say, well, if at nighttime after these images, I can inform the firefighter to say, go, we have to kill the fire in these regions because those regions are in the flaming. And if the wind coming down here, it will make the fire growing in these areas, not in those areas because it's smoldering. So it turns out in the daytime, you can see from satellite, those are the fires we see from the satellite in the daytime. Kind of resonates what we try to predict. So I think there's a lot of potential for this product here. How am I doing here? Well, I still have about 20 minutes, so I will share with you some other work we have been doing with the fire. So fire, one part is emissions. We want to know the emissions. We want to know the combustion efficiency, and we want to know how much CO2 are released by the fires and such. And we want to know how we can provide better information beyond just the location of a fire to the firefighters to help surveillance monitoring and such. But once a fire occurred, they will emit a large amount of smoke particles into the atmosphere. And when the weather conditions permits, they will be transporting downwind for thousands of miles. So one question is that during the transport, when will they touch down to the surface affects the air quality, and how long will the plume transport, right? If the plume are pretty low, then they're not going to transport very long. If the plume are very high, they can transport pretty long. So we want to have a capability to detect the small plume height from the space. So we are going to use a satellite called the EPIC aboard a satellite called the Deep Space Climate Observatory. This Discover. Discover is a satellite that was launched in 2015 and is parked in a point called Lagrange 1 point. At this point here, the force from the sun and the force from the earth will generate a confipedal force that is needed for satellite just stay here. And then suddenly it moves around, right? As the earth moves, it moves around. In other words, this is basically a three-body balance problem, balance situation. So this guy basically always constantly looking at this platform, the satellite, we're constantly looking at the sunlight reflected by the earth. And it also always have the sun behind the satellite. They are on the same line, and this is orbit right here. That point here is called Lagrange 1 point. In the universe, actually, there are 5 of those guys, right? Where the force between the sun and the earth generate a centripetal force that is imbalance, okay? Anyway, you can actually solve this by using physics, okay? But anyway, the point here is that you also have a moon right here, right? That's our moon right here, okay? So the idea here, this one is actually really not meant to be observing the Earth. It's meant to be detect the solar wind. So on the other side of the platform, they are constantly looking at the sun. But on the back side of the platform, like we can constantly look at the Earth. Every hour, you can look at the 50% of the Earth surface that is lighted by the sun. It takes us about almost 6 months to get to there, right? It's 1.5 million kilometers away from that. But anyway, it has 4 bands, and then and they also have 6 visible channels. So there are quite a bit of the bands here. So here I'm showing some images that's really cool, just to illustrate you that you may not able to see it a lot. So this actually showing the other side of the moon that we normally will not see. When we raise our head, look at the moon, we only see the back side of the moon. Or depending how you say it. Okay, this could, if you were standing on the Earth, this basically showing the back side of the moon, right? That's the facing the sun that we don't see that much, too much. Okay, you can also see the solar eclipse, right? Every hour. These are North America solar eclipse. You can see also solar eclipse in Asia. And so there are a lot of good, interesting things coming out from this satellite here. So we are interested in something called the oxygen absorption band in the in satellite right here, in the equivalent by the satellite. So oxygen absorption band actually there are 2 or a little bit more too. Primarily, we're interested in 2 oxygen absorption band. One is in the oxygen A band. This is A band, and one is in the B band. So when you look to the top atmosphere radiation, the radiation coming from the sun, that's this curve right here. But when you look at the solar radiation at the surface, that's what you have in here. You see many times the radiation in certain wavelengths coming from the sun will never reach to the surface. Why? Because you got water absorptions. You got other gases that absorb them. It turns out that the oxygen, most time, that does not absorb. But there are 2 bands that actually absorb the radiation. The gas optical depths for oxygen B can go up by 10 in certain wavelengths, where gas absorption optical depths for A can go up to 100. So in other words, in those narrow bands here, the light, the radiation in those wavelengths is very difficult to get into the surface. You can look at the penetrated depths here. Those light goes to here from the top atmosphere. They only penetrate about 15 kilometers in the atmosphere, then it's gone, absorbed by oxygen. Certainly, this one is getting higher. So I maybe have this one swapped. But the point is that certain of the radiation at certain wavelengths will be absorbed by the oxygen molecular before they reach the atmosphere. So we want to use this principle to detect the aerosol plume height passively from space, not using LiDAR, but just using sunlight. So the idea here is that if there is no absorption, right? You have aerosol plume right here versus aerosol right here. This one is higher than this guy. Because there is no gas absorption, therefore the same scattering by the same plume will return the same amount of the light. Therefore, in this case here, I1 will be equal to I2 in the alternate window channels where you don't have gas absorption. On the other hand, if you got the oxygen absorption, then if your plume is higher, then you will reflect more relatively compared to another one, plume is lower, back to space. Because when you have the aerosol plume is higher, you intersect this light and reflect back to space. As a result, you prevent more oxygen down below to absorb this light. Where if you have aerosol plume is lower, you provide opportunity for more oxygen to absorb before you reflect back to space. Therefore, these two difference, right, compared to the one in the nearby channels where you don't have aerosol absorption, compared to this guy, the ratio will give you an indication of the altitude of the aerosol plume. So that's kind of physics right there. So we use the two bands here, right? This is oxygen A band, this is oxygen B band. Because oxygen B band, the surface reflectance is much lower than oxygen A band. So you can see for the most part is below 0.1. So we use O2B band to detect the aerosol layer height over the land surfaces, because we don't want this one to be so reflective, right? Brighter is more difficult to detect the aerosols, brighter surfaces. So give you some idea here. Here is a image. What I'm showing here is from discovery in 2017, 2 days, August 25th, August 26th, and in different times. This is 1 hour apart. This kind of a right here. Oh, sorry. These are 2 days. These are the 3 hours, and this is just 1 hour, just to illustrate, give you idea here. So this is what we plot the aerosol layer height. We retrieve that based upon the oxygen B band. And here is our aerosol depth. Here is the surface observed PM 2.5, which you care because that affects the quality of air you breathe. What you find is that in those cases here, you can see the smoke plume is rising, and I'll eventually get to here. This means the smoke plume is rising. As a result, you can see in these areas, surface PM does not affected by those, right? I mean, the PM 2.5 is pretty low all the time. Why? Because as smoke is up in the air, it's not going to affect the quality of air we breathe. But on the other hand, if you look at these areas here, some other areas, like these areas, and some other low areas, okay? And you can start to see the aerosol layer height is actually, this might be shifted a little bit. Oh, right here. Look at this guy right here. Okay, very low aerosol height, right? Goes to about less than 2 kilometers. And then you look at the AOD here is also high. And guess what? The air quality is bad. The PM2.5 will increase a lot. So that provides you the kind of the one piece of information that we normally don't get from the satellite. That is the vertical dimension of the plume. And that's very valuable for us to predict the PM 2.5, to analyze the PM 2.5 to help model evaluate how they are doing, because the model don't know where to put the smoke plume height in the model. Most satellite observation only give us two-dimensional knowledge. So we also compare that with the LiDAR called Calypso, right? Calypso certainly is a LiDAR that is coming down and start to probe the altitude of the aerosols in different altitudes. So it's a lighter, therefore you get a very detailed structure. And our technique can only give you one piece of information. We call them aerosol layer height, defined as this one here. Okay. Anyway, so you can see that our one information to describe the aerosol layer height is very consistent with the CLIPS observations, right? We don't give you detailed vertical structure, but at least we can tell you if that aerosol layer height is where it's located roughly. We will find that this area is around half kilometer to 1 kilometer range. That's actually pretty good in many ways. Most of them are in the half kilometer range. So we're now using, because the EPIC, this discovery is so far from the Earth, right? 1.5 million kilometers from the Earth. So their footprint is pretty big. It's like 24 kilometers, too big. So if there is a tiny bit of the clouds within that pixel, that will affect our signal to detect the aerosol layer height. So we are now using this technique to apply to a satellite sensor called TROPOMI, which is launched by Europe. And they have much finer resolution, like 4 kilometers. And they also have the O2B band. So this is kind of a very kind of a new results here. Now you can see better of the smooth plume in these 3 days. And we are able to, on top of it, we are able to plot the surface PM2.5 and also we retrieve the aerosol layer height. You can see, like in here, aerosol layer height is very high, 6 kilometers. You can see the surface PM2.5, very low. Similar is here, very low. Here, very low. Although there are smokes, the LOD could be very high. There are smokes definitely, but this smoke does not affect air quality. So we are now, and we also compare that with the LiDAR data, and you can find our agreement agrees pretty well. So this is our algorithm. This is the algorithm that from Europe, the standard algorithm. You can see there have a huge amount of the overestimation. So I think our algorithm is unique because we are using the O2B band where the surface reflectance is low. Where here they are using the oxygen A band, surface reflectance is so high, and they have other things need to be fixed, I think. But more or less, you get a flavor is that we're able to now track the aerosol plume height, smoke aerosol plume height from the west coast down to the east coast, and that's kind of very wide coverage, spatial coverage, where the traditional LiDAR only give you one pattern, one pass here, that's it. So in summary, we have developed the algorithm to quantify the fire combustion efficiency at nighttime, because in the daytime, the solar radiation visible light is so strong, it smears our signal. So we have not looked into that yet in the daytime, but nighttime certainly seems pretty promising. And we also developed research algorithms that can retrieve the smoke aerosol layer height from space. And that seems to have a lot of potential to help us to understand the degree to which those fires may affect the air quality downwind through the long-range transport. Sometimes they do, sometimes they don't, depending on altitude. And we have a we have an algorithm to kind of provide some information for that. So we're going to keep working on those lines and to try to continue evaluate this parameter here, and then better refine the algorithm, also detect, for example, dust over the land, the dust plumes over land, and things like that. So I looking forward to have more collaborations. I'd like to thank you for inviting me, and the NASA and the Navy for providing the funding. I have one last slide, I believe. This is kind of a task for every faculty here in the department here now, is that we're always looking for students to work together, okay? So here is my website, our department website, here's my group website. Here is some benefits you get. We fully waive your tuition for graduate studies. We pay about 32K per year stipends for our students, and you will enjoy the full insurance benefits and such. But probably more exciting is that if this research excites you, then that's something we can talk about. I'm looking forward to that. Thank you. Yeah.
Yeah, if we were all in person, we would be loudly applauding. But thank you so much, Jun. That was wow, that was excellent. Other than trying to steal away our students, but you know, I learned a lot about VIIRS that I didn't realize before. And the work with the EPIC data is very interesting, and some of those visualizations were quite interesting. So we have time for a few questions if folks either want to chat something in the chat box, or if I think you can unmute yourself. If you can't, I can unmute you if you want to ask a question. But while we're waiting, if there's other questions, I was really impressed by just how much imaging science is in the talk that you gave. And in particular, the thing that jumped out at me was the subpixel effects and the misregistration between the day-night band and the thermal bands, and the work that you had to do on the VIIRS data to be able to back out that visible energy fraction at night. And so I guess a couple questions about that. So I know that NOAA, as they produce these products, they go through a lot of work, I thought, to produce a georegistered product. And so my question is, are you using more of a raw level data, or is their georegistration just not accurate enough to do the kind of work that you're doing?
Well, John, you asked the question you asked is right on. I had a thought. Let's see here. I had a thought when we started this one, I had a thought that would be pretty quick, right? We should be able to do this pretty quick. Actually, this part turns out to be the most heaviest job for the student. The reason is because this VIIRS is this S that stands for suite of the sensor. So it's a suite. They have 5 I band and 16 M band. So what happens is that when those band, sorry, I probably cannot draw it here. Okay, illustrate it here. So when those band start from near, when they start to do the scanning, the pixel size increases.
You might have to swap displays. We're seeing your preview.
Oh, sorry.
Yeah.
Oh, okay. Can you see it now?
Now we're seeing it, I think. Yeah, so you were drawing on the screen, right?
Yeah, I tried to draw it on the screen. Yeah. Okay. Yeah, so what I'm saying here is that you can see for this I band or M band, it's in the nadir. Now, when they scan toward the edge, the pixel size increases. They each scan have 16 detectors, okay, and they go like that. So DNA band, on the other hand, is different. DNA band is a 2-dimensional CCD array. They give you something like this. You know what I'm showing here is that. So as a result, it's not like the NOAA is not doing a good job to georeference the location of the pixels from DNA band or either of these bands. They do a good job of that. But the point I want to make here is that let's say I have a pixel right here, and then I may have several couple of the DNA band pixels right here. So the point is that if I have a fire in here, how much light I'm getting from this fire pixels? Well, you have to come with, we say, well, we'll do an area average from these 4 pixels, then we'll get the light for this pixel. That's perfectly fine. However, when you start to think about a global algorithm, and you want to do this effectively, align every pixel, not just the 5 pixels, but every pixel, and conform them with the dynamic pixel, conform the dynamic pixel to each of the M-band pixel, then computationally will be very heavy because each of these pixels, their alignment is different along the lines. And there are thousands of those guys, thousands of those pixels. So we come up with a lookup table method by understanding the mechanics of those scan mechanics. So that spent a lot of time to do that. There is one other thing I want to make sure I want to talk about is that those IBN pixels, their age, their increase, pixel size increase from the netter to the edge is only a factor of 2. The reason is because they are throwing out a lot of pixels. In the netter, let's say you got a detector here, right? So you average 3 of them. You make them 1 pixel. But in the meter, when it grew bigger, okay, when it grew bigger, in order to keep the relative size of the pixel, you throw one of them away. This one goes away. When you then get to the edge, you only have 1 pixel left. So that's through a lot of the pixels. As a result, you really have to know the mechanics of how the hardware work in order to get this or get this dynamic pixel to align with the VIIRS pixel and actually match very well for the fire research, because fire is very localized. So yeah.
That's fascinating. So the problem is not so much in the positioning of the pixels, you know, the registration is okay, but it's actually the ground instantaneous field of view, or how much area each pixel is seeing, and relative between the 2 different bands, because you need precise alignment of the area on the ground that is being imaged within that pixel, not just its position, but how large of an area, because you're doing such quantitative calculations at the single pixel level. And that's the other aspect, is there's so much radiometry in what you're doing. And our first year grad students are immersed in their radiometry course right now. So this is all very, very relevant. Well, I think we've reached the end of the hour, and I don't see any questions popping up, but I'm sure that Jun would be willing to engage in email or follow-up conversations with folks. He's easy to find at the University of Iowa website. And yes, thank you so much for taking the time. And just so folks know, we have started some discussions about possible collaborations and working on proposals. So this is an exciting area. Okay.
Well, thank you so much, John, to and everybody on the call to have me. You know, we definitely it's a good time to exchange, and I look forward to have more follow-ups. Yeah. Okay, great. And thanks everyone for joining. And with that, we'll end the seminar. Okay. Take care. Okay, take care. Yeah, bye.